Near the edge of what stars can physically be, one giant pushes every known limit, V766 Centauri Aa, a blazing, swollen monster with a size and power that challenge our understanding of stellar physics. Tonight we'll explore what makes this star so extreme. If you enjoy the journey, please like, subscribe and share, and tell us in the comments what's the most mind-blowing star you've ever heard of. Thank you for watching. Now let's begin. The Milky Way appears as a soft pale band across the night sky, yet as astronomers study it, this band resolves into a vast barred spiral galaxy with a flat rotating disk, a central bulge, and a more diffuse halo of older stars surrounding everything. Within the disk, gas, dust and stars gather into a delicate pattern of spiral arms that wind slowly around the center, where the massive object called Sagittarius A star sits deeply buried in crowded stellar layers and clouds. The Sun lies in one of the quieter stretches of the disk orbiting the center at a distance of many thousands of light years, but the brightest and most short-lived stars prefer more active zones, especially along the inner parts of the spiral arms where the raw material for star formation is concentrated. In these regions, great clouds of cold molecular gas drift through the disk, occasionally compressed by passing spiral patterns, by winds from earlier generations of hot stars, or by the shock fronts of exploded stars. Where the gas becomes dense enough, gravity overwhelms internal pressure and draws the cloud inward, causing it to fragment into clumps that will each contract into a new star. Most of the resulting stars are modest in mass and luminosity, but a small fraction at the upper end of the distribution gather far more material and become the giants of the galaxy. These very massive stars shine with a brilliance tens of thousands or even hundreds of thousands of times greater than that of the Sun, and their intense radiation and fierce stellar winds quickly reshape the birth cloud around them. They live fast, using up the nuclear fuel in their cores in only a few million years, and they rarely wander far from the nurseries that produced them. Because their lives are so short, the galaxy contains relatively few at any given time, yet they contribute a significant share of its ultraviolet and visible light, and they play an outsized role in stirring and enriching the interstellar medium. Among these luminous giants, some evolve into supergiants and hypergiant stars with bloated envelopes that extend far beyond the kind of stellar surface familiar from more ordinary stars. A supergiant or hypergiant is a very massive star that has expanded and cooled at its outer layers, while remaining intensely hot and bright at its core, so that its atmosphere becomes unstable and prone to strong mass loss. The star's light pushes outward on its own outer layers, while gravity pulls inward and near the balance point. The outer envelope can become tenuous, irregular, and dynamic. In the most extreme cases, the outward push from the light coming from the interior almost equals the inward pull of gravity, leaving the star close to the practical limits of size and luminosity that stable stars can reach. Such extreme stars do not appear at random locations within the Milky Way. They trace out the structure of the disk and its spiral pattern, because they form where gas densities and triggering events favour the birth of very massive stars. Their distribution follows the midplane of the disk, hugging the thin layer where cold gas and dust are most common, and clustering, especially in the inner spiral arms, where conditions are most favourable for intense star formation. Viewed from inside the galaxy along the plane of the disk, this concentration reveals itself as crowded star fields, glowing nebulae and distant clusters projected against one another, especially in the part of the sky where the inner spiral arms of the southern Milky Way cross the line of sight. Constellations such as Carina Crux and Centaurus sit along this luminous band, and within their borders the night sky hosts some of the most energetic and short-lived stars accessible to detailed observation. In these directions, the line of sight passes through multiple layers of the disk intersecting different spiral arms at different distances so that foreground stars, background stars and distant clusters all overlap. Dust in the disk reddens and dims the light from more distant objects, so some of the most powerful stars in the galaxy do not stand out to the unaided eye, even though they pour out extraordinary amounts of energy. Astronomers rely on careful measurements of distance, color brightness, and motion to pick out these rare giants and to place them within the three-dimensional structure of the Milky Way. By combining spectroscopic data, which reveals temperatures, surface gravities, and chemical compositions with models of stellar evolution, they can sort ordinary bright stars from those that lie close to the upper limits of known stellar size and luminosity. The pattern that emerges shows that extreme stars tend to favor large star-forming complexes along the inner arms, where gas clouds are massive and dense enough to give rise to clusters containing many high-mass stars. Within these complexes, a few exceptional objects stand out by pushing close to the boundaries set by the balance of radiation and gravity in stellar envelopes. Somewhere in the inner regions of the southern Milky Way, in the direction of the constellation Centaurus, and at a distance of several thousand light-years from the Sun, one such extreme, swollen and highly luminous star lies embedded in a busy stretch of the disk. It is one member of the small family of stars that approach the known limits of size and brightness for a star supported by its own internal nuclear fusion, and its presence marks a place where the interplay of galactic structure, gas dynamics, and stellar evolution has produced a rare example of a stellar giant crowded up against the edge of what the Milky Way can sustain. Over long times, the motions of gas and stars in the disk carry such giants around the galactic center, yet their brief lifetimes ensure that they trace only small arcs of these paths before ending in collapse or explosion. In this way, each extreme star becomes a short-lived marker of the conditions that prevailed in its birthplace, a luminous signpost written into the structure of the Milky Way by the combined action of gravity, rotation, and starlight. Within the disk of the Milky Way, the spiral pattern does not form a set of sharp, rigid arms, but rather broad, gently curved regions where the density of gas dust and young stars is slightly higher than average. One of these great structures is the Centaurus spiral arm, an inner arm that winds through the southern sky and carries some of the most active star-forming regions in the nearby part of the galaxy. In this arm, clouds of cold molecular gas extend over hundreds of light-years, threaded by filaments and knots that respond to gravity turbulence and the passing wave of the spiral pattern itself. As the spiral density wave sweeps slowly around the galaxy, the gas inside the arm responds by compressing and forming new stars. Behind the wave, the newborn stars drift away while the gas thins and stretches into less dense regions between the arms. From the vantage point of the Sun, which lies in a more modest spur between two larger arms, the Centaurus arm appears as a bright, crowded lane near the plane of the disk, especially in directions where the line of sight crosses the inner galaxy. In those directions, the path through the Milky Way cuts across several layers of structure, moving from local interstellar space around the Sun into more distant gas and stars associated with the inner arms, and eventually toward the regions nearer the galactic center. Because light from those distant regions must pass through many intervening clouds of dust, the stars in the Centaurus arm do not always display their true brightness or color to human eyes. Dust grains in the interstellar medium absorb and scatter short wavelength light more efficiently than longer wavelengths, so distant stars appear redder and dimmer than they would if seen without intervening material. This effect, called interstellar reddening, complicates attempts to read the properties of stars by simple inspection. In the Centaurus direction, reddening is often severe because the line of sight passes through multiple dusty regions. Astronomers therefore rely on careful measurements in several colours, combined with models of how dust interacts with light to estimate the amount of dimming and to reconstruct the intrinsic luminosity and temperature of stars projected on this arm. When these corrections are applied, some objects that appear as modest points in the sky are revealed as powerful sources shining with enormous energy, but buried behind thick curtains of dust. The Centaurus arm carries a mix of stellar populations. Older stars born long ago in earlier phases of the arm drift in elongated orbits that carry them somewhat away from their birthplaces, but younger stars tend to remain closer to the dense gas structures that created them. In some places, compact open clusters hold together dozens or hundreds of young stars whose ages and motions still reflect the conditions in the cloud from which they formed. Massive stars in these clusters flood their surroundings with ultraviolet radiation, ionizing the gas and producing glowing nebulae that trace out bubbles and arcs around the clusters. Winds from the hot, luminous stars blow cavities into the gas-piling material into shells that can themselves become sites of secondary star formation. Over time, successive generations of massive stars carve layered structures in the arm, so that an observer looking through the Centaurus region sees overlapping nebulae and associations at different distances and ages. Embedded within this complex scene are regions where the gas and dust are particularly dense, forming large molecular cloud complexes that stretch over many tens or hundreds of light years. In their interiors, shielded from harsh radiation, temperatures can fall low enough for molecules to survive, and for gravity to slowly gather mass into clumps. Some of these clumps will form only low-mass stars, but in the largest and most strongly compressed regions, a small number of very massive stars come into being. These young giants quickly begin to dominate the energy budget of their neighbourhoods, heating the gas, altering its chemistry and driving further evolution of the cloud. In the Centaurus arm, several such cloud complexes sit at distances of a few thousand light years from the Sun, arranged roughly along a curve that marks the inner edge of the local spiral structure. They are not evenly spaced. Rather, they appear where converging flows, shocks, or historical events have produced particularly favourable conditions for star formation. Radio observations of molecular lines reveal their masses and internal motions, while infrared and submillimeter studies probe the dust and deeply embedded protostars that cannot be seen at visible wavelengths. Together, these data build a three-dimensional map of the arm segment showing where dense gas-young clusters and luminous evolved stars lie relative to one another. Against this mapped structure, the brightest members of the arm emerge as waypoints. Some are hot blue stars that have not yet evolved, far from the main phase of their lives, emitting strong ultraviolet light and generating fast tenuous winds. Others are stars that have exhausted the simple core burning stage and have swelled into enormous cooler envelopes, becoming red or yellow supergiants and hypergiants, whose surfaces drop in temperature even as their total luminosities remain extreme. These swollen stars radiate huge amounts of energy from very large surfaces, and their outer layers become unstable, leading to episodes of heavy mass loss. In optical images, such stars can appear heavily reddened and sometimes surrounded by faint nebulosity. In infrared views, their dusty shells glow more strongly, revealing the material they have expelled. The Centaurus arm contains several such luminous giants, scattered among the clusters and nebulae that occupy this busy segment of the disk. Although they may appear isolated when examined in a small field, they are in fact part of a broader tapestry of star formation and evolution that stretches along the arm. Each massive star began as a core within a dense clump of molecular gas. Each has already altered its surroundings through radiation and winds, and each is destined to end its life relatively soon in astronomical terms. The presence of multiple such objects in the same arm segment suggests that the underlying molecular complex was capable of forming an entire population of high-mass stars, some of which are still near the hot youthful stage, while others have already expanded and cooled into more fragile extended states. From the standpoint of galactic structure, this makes the Centaurus arm an important laboratory for studying how the most massive stars are born, how they interact with their environment, and how they approach the physical limits of stability. Somewhere along this inner arm, in a direction where the dust is thick and the fields of view are crowded, lies a region where the combined action of gravity-gas dynamics and rotation has produced not only hot blue stars and ordinary bright giants, but also at least one object with an envelope so extended and luminous that it challenges the boundaries set by known stellar physics. The broader context of the Centaurus arm, with its layered clouds, overlapping clusters, and complex flow of gas, provides the stage on which that extreme star has formed, evolved, and begun to shape its own surroundings in turn. Among the many star-forming complexes threaded along the Centaurus spiral arm, one region stands out as a broad, faint ring of ionized gas set within a larger body of cold molecular material, an evolved bubble where earlier generations of massive stars have already done much of their work. This region is known to astronomers as a nebula formed from hydrogen that has been stripped of its electrons, an ionized hydrogen region that glows softly where energetic radiation has illuminated the gas. Around it, the parent molecular cloud still persists a vast reservoir of cool, dense material from which stars have formed in the past and continue to form in the present. Seen at visible wavelengths, the ionized nebula appears as a dim, uneven shell, its edges traced faintly against the background of the inner Milky Way, while dark lanes and patches of dust obscure parts of the field and give the impression of gaps and filaments. Infrared observations, which are less affected by dust, reveal a more complete picture, showing a ring of emission, where the interface between hot ionized gas and cooler neutral material is rich in small dust grains and complex molecules. This ring marks the place where ultraviolet light from massive stars has eaten its way outward into the surrounding cloud, leaving behind a cavity of thinner, warmer gas and compressing the cooler layers just beyond the boundary. The region is not young in the sense of a freshly lit nebula around newly born hot stars. Analyses of its size, structure, and stellar content indicate that the original ionizing stars were born several million years ago, and that they have already evolved away from their earliest, hottest phase. In its youth, the nebula is thought to have been brighter and more sharply defined, with a stronger flux of energetic photons carving a larger cavity in the cloud. Over time, as the massive stars aged and cooled, the intensity of their ionizing radiation declined, and the expanding bubble slowed, leaving a more quiescent ring of ionized gas wrapped around a partially refilled interior. The present structure thus records both the initial burst of activity and the subsequent evolution of the central stars. In the cavity's interior, the gas is warmer and more diffuse than in the surrounding cloud, its density reduced by the combined action of radiation pressure, stellar winds, and earlier expansion. Closer to the shell, the gas becomes denser again, and the boundary region where ionized and neutral material meet forms a photodissociation zone rich in emission at mid-infrared wavelengths. Beyond this boundary, the cold molecular cloud continues containing clumps and filaments that represent both residual structure from the original cloud and new condensations triggered by the expansion of the ionized region. This triggered aspect appears in the distribution of young stellar objects around the ring. infrared surveys detect small clusters and individual forming stars embedded in the compressed layers at the nebular edge, some of low mass and some of higher mass, indicating that star formation is still underway long after the first generation of massive stars began to clear their surroundings. The ages of these young stars, inferred from their spectral energy distributions and positions in infrared color diagrams, suggest several episodes of formation over an extended period, consistent with a picture in which the expansion of the nebula and the reorganization of the cloud created new sites of collapse. In this way, the region becomes a record of multiple linked generations, with the earliest massive stars leaving behind a cavity and a ring, and subsequent stars forming in the swept-up layers and in residual dense clumps. The entire structure sits within a larger molecular complex that stretches along the Centaurus arm at a distance of roughly a few thousand parsecs from the Sun, part of a chain of star-forming sites that share similar velocities and chemical properties. Radio observations of molecular lines trace the distribution of dense gas, showing that the ionized cavity is carved out of one portion of a more extensive cloud, rather than existing as an isolated object. The kinematics of the gas indicate that the region has expanded and evolved over several million years, but has not completely disrupted the parent cloud, leaving plenty of material available for further star formation. Within and around the cavity, smaller subregions show their own structures, compact knots of emission where localized clusters are forming, elongated filaments that bridge the boundary between ionized and neutral gas, and faint arcs or pillars where denser clumps resist erosion and cast shadows into the interior. These details reveal how uneven the interaction between massive stars and their environment can be, and how local conditions shape the exact pattern of feedback. In some directions, the ionized gas has broken out more freely into lower density surroundings, producing more extended faint emission. In others, it remains confined by thicker segments of the cloud. Against this evolving backdrop, a few very luminous stars stand near the center of the cavity, heavily reddened by dust but dominating the energy budget of the immediate environment. Their past radiation appears to have been sufficient to ionize the nebula on the scales observed, and their present properties mark them as evolved descendants of the early massive population that first lit the region. Their space motions derived from proper motion, and radial velocity measurements match those of the nebula and its associated molecular cloud, supporting the conclusion that they were born here rather than merely projected against the complex by chance. Over time, as these stars age further and lose more mass, they continue to alter the conditions inside the cavity, contributing additional material to the already enriched gas and adding new structures to the dusty envelope that surrounds the central area. The open cluster seen nearby in projection, with its own bright stars and well-defined main sequence, lies at a significantly closer distance and represents a separate star-forming event in the foreground, reminding observers how easily different layers of the galaxy can overlap along a single line of sight. For the nebula itself, however, the true physical companions are the young stars forming in the compressed ring, and the evolved massive stars near the center, which together trace the life cycle of the parent cloud from initial collapse through energetic feedback to ongoing secondary formation. In this star-forming complex, the interplay between ionized gas, neutral molecular material dust, and luminous stars has already played out over several million years, yet it is still incomplete. The ring of ionized gas continues to glow, the boundary regions continue to host new stars, and the massive evolved stars at the center continue to shed mass and shape their surroundings. It is within this extended and intricate environment, sculpted by earlier phases of massive star evolution and sustained by a large reservoir of cold gas, that one of the most extreme and swollen stellar objects known in this part of the galaxy now resides embedded not as an isolated curiosity, but as one outcome of the long complex history of the GUM-48d molecular cloud. Seen at higher resolution, the star-forming complex in this part of the Centaurus arm reveals itself not as a single structure, but as a layered scene of clouds associations and clusters that overlap along the same line of sight. The evolved ionized ring and its parent molecular cloud occupy only one of these layers. In front of and behind them, other pieces of the galactic disk contribute stars and gas that project into the same patch of sky but do not share the same physical space. Separating these contributions is essential for understanding which stars truly belong to the environment carved by the evolved nebula and which are only superposed. Near the projected center of the ionized cavity, a concentration of bright stars stands out in visible images as a small group of luminous points framed by diffuse emission and dark dust lanes. At first glance, it might be tempting to treat all of these bright objects as members of a single compact cluster at one distance. However, detailed study shows that the situation is more complex. Some of the blue-white stars in the field have relatively small reddening, meaning that their light has not passed through as much dust. Their measured motions across the sky and their distances inferred from parallax and photometry place them significantly closer to the Sun than the molecular cloud complex and the evolved ionized region. These stars gather into a foreground open cluster, a loose gravitationally bound group formed in an earlier event in the nearer parts of the galactic disk. Its members share similar ages and chemical compositions, and their positions on the diagram that relates brightness and temperature follow the pattern expected for a cluster at a moderate distance with only modest extinction. Although this foreground cluster appears near the nebula in projection, it does not participate in the dynamics of the evolved cavity, and does not contribute to the ionization of the gas. Behind or within the plane of the ionized bubble, other stars show heavier reddening and different brightness patterns, indicating that they lie deeper in the disk and closer to the molecular cloud that hosts the evolved region. Among these are a small set of luminous stars whose colors and spectra mark them as massive evolved objects, and a larger population of lower mass stars at various evolutionary stages. Infrared observations pick up still younger objects heavily embedded in dust and gas, whose light at shorter wavelengths is almost completely blocked. These embedded sources cluster along the compressed ring and in dense knots at the periphery of the cavity like beads along the edge of the ionized shell. Their distribution suggests that they have formed from material swept up and rearranged by earlier activity in the region. Some of the embedded clusters are small, containing only a handful of young stars, while others host dozens or more along with diffuse emission from warm dust that traces out the structure of the compressed layers. The velocities of gas and stars in these locations match those of the evolved nebula and the surrounding molecular complex, indicating that they share a common distance and history. In addition to the embedded groups, there are more widely scattered young stars in the vicinity, some with circumstellar disks that still radiate strongly in the infrared. These objects represent a more dispersed component of the recent star formation, less tightly tied to specific dense clumps, but still born from the same reservoir of molecular gas. Together, the compressed ring clusters and the scattered young stars compose the most recent generation in the region, superposed on the longer-lived population of older, lower-mass stars that pervade the arm. Beyond the immediate environs of the evolved nebula, the larger molecular cloud complex hosts other star-forming sites at slightly different velocities and distances, though still broadly associated with the same segment of the spiral arm. These sites include compact infrared sources, small H2 regions around younger hot stars, and dark filaments, where gravitational collapse is still underway. The cloud as a whole shows evidence of having been shaped by multiple feedback events over millions of years, with cavities arcs and bright rims marking places where massive stars have injected energy into the gas. The evolved ionized ring, in which the current luminous evolved stars sit, is just one of these structures distinguished by its age and by the advanced evolutionary state of its central sources. Superposed on all of this further out along the line of sight lie still more distant stars and possibly other nebulae associated with inner parts of the spiral arm or with separate structures such as supernova remnants. Their contributions complicate the appearance of the field, but can often be separated through careful analysis of their velocities, reddening and spectral types. In practice, astronomers tease apart this layered scene by combining several kinds of measurement. Photometry in different wavelength bands reveals how much dust extinction affects each star, while spectroscopy provides radial velocities and spectral classifications that constrain temperature and luminosity. Astrometric data give proper motions and, when precise enough, direct distance estimates. By assembling these pieces, researchers can sort stars into foreground clusters, genuine members of the evolved nebula's environment, and more distant background objects. In the immediate sky region under consideration, this process shows that the prominent nearby open cluster belongs to the foreground and does not share the distance of the evolved ionized bubble and its central luminous stars. The stars responsible for carving and sustaining the nebula are instead part of a more diffuse and irregular group embedded within the molecular cloud, accompanied by the younger objects forming in the compressed shell, and by a broader sprinkling of associated stars spread through the cavity and its surroundings. The present-day environment of the evolved ionized region is therefore not a simple spherical shell around a single cluster, but a composite structure. It includes a foreground cluster that only appears connected an aging group of massive stars, and their less massive companions genuinely linked to the cavity and fresh sites of star formation, tracing the current interaction between radiation winds and dense cloud material. Nearby clouds range from cold dense filaments still collapsing under gravity to warmer, more diffuse gas in the interior of the cavity, while neighbor clusters span a range of ages and distances. This environment provides the broader setting for the central evolved stars that now dominate the energy output in this part of the cloud, and it frames their contribution to the ongoing transformation of gas into new generations of stars along this segment of the Centaurus arm. At the heart of the evolved nebula and molecular cloud complex, the small stellar group, designated HR 5171, gathers several luminous stars into a loose association that now dominates the energy output of this part of the Centaurus arm. The group is not a dense spherical cluster, but rather a compact arrangement of massive evolved stars embedded within the broader field of young and older objects that share the same general region of space. Among these, the most striking is the swollen, cool, and highly luminous star known as V766 Centauri Aa, whose extended outer layers and heavy reddening cause it to appear as a bright but unusually coloured source whenever the line of sight is not completely blocked by dust. Nearby, at a much smaller angular separation than most of the surrounding field, lies a hot blue star of supergiant type, HR 5171b, which shines with intense ultraviolet light and contributes significantly to the ionization and heating of the local gas, even though it appears several magnitudes fainter in visible light than the cool giant. Together, these stars, along with less massive companions and younger forming objects in the surrounding compressed ring, form a small but powerful system that has already altered the structure of the gas and dust in its vicinity. The spatial relationship between the swollen, cool primary region and the hot blue companion becomes clearer when the system is studied across multiple wavelengths. Invisible light heavy reddening caused by interstellar and circumstellar dust dims and reddens the emission from both stars, but the cool luminous star suffers especially strong extinction because much of its light emerges at shorter wavelengths where dust absorption is more severe. As a result, it does not stand out as dramatically as its intrinsic luminosity would suggest, and the blue companion can appear closer in brightness than the raw energy output of the two stars alone would predict. In the infrared, however, the balance changes. The cool star's extended envelope radiates strongly at longer wavelengths, both through the direct thermal emission of its outer layers and through the glow of warm dust grains that have condensed out of the material shed by the star. Infrared images show a bright centrally concentrated source surrounded by a halo of emission, within which the cooler gas and dust of the molecular cloud are partially heated and reprocessed by the combined radiation of the whole system. The blue supergiant, by contrast, remains relatively compact and hot, its radiation peaking in the ultraviolet and visible ranges. It lacks the same level of extended dusty envelope, and therefore contributes less to the infrared brightness of the region, even though its total luminosity is still extremely high by the standards of ordinary stars. Spectroscopic observations disentangle these contributions by separating the composite light into its constituent colours. The cool star imprints a spectrum characteristic of a very luminous late-type supergiant with strong absorption features from neutral metals and molecules in its extended atmosphere, as well as emission features formed in a dense stellar wind. The blue companion adds a second set of lines associated with a hot early-type supergiant including strong hydrogen and helium features and signatures of a powerful fast wind. In some wavelength ranges the spectra overlap and must be modelled as a combination of two luminous sources seen through a common veil of dust. In others, careful choice of diagnostic lines allows astronomers to trace the properties of each star separately, confirming that both are very massive and that both have already evolved away from the simple main phase of hydrogen burning in their cores. The positions and motions of these stars within the nebula support the conclusion that they are physically associated with the evolved ionized region rather than being chance alignments. Their radial velocities and proper motions match those of the surrounding gas to within the uncertainties of current measurements, and their inferred distances, although not perfectly constrained, are consistent with membership in the same segment of the Centaurus arm and the same molecular cloud complex. The ionized nebula's size and age imply that several million years ago, at least one very hot massive star, and possibly more than one, produced enough energetic radiation to carve the observed cavity in the cloud. The present combination of a cool, swollen, evolved giant and a hot blue supergiant at the centre of the cavity fits naturally into this picture as the aging descendants of that early massive population. Whether all of the original ionizing stars are still present, or whether some have already ended their lives in supernova explosions remains uncertain, but the surviving luminous members clearly continue to shape the environment. Their combined radiation maintains the ionization of gas in at least parts of the ring, while their winds and past mass loss episodes feed additional material into the dusty envelope that fills the cavity's interior. The geometry of the system is complex. The cool, luminous star and the blue companion are separated on the sky by only a few arc-seconds, yet their physical separation in space is much larger, likely tens of thousands of astronomical units if they lie at the same distance. This makes their gravitational interaction on short timescales relatively weak, compared with the more intimate interactions that occur in close binaries, but their combined radiative and mechanical influence on the shared environment is strong. The blue supergiant's hot wind blows a cavity within the already rarefied gas, while the cool star's slower but denser outflow supplies dust and molecules that can be shaped and illuminated by the companion's radiation. At the same time, both stars sit within the broader flow of material moving through the evolved nebula and the parent molecular cloud so that their local actions are embedded in larger-scale motions and structures. Observations at radio and submillimeter wavelengths detect emission from molecular species and dust grains in the vicinity of the system, indicating that the central stars are not isolated in empty space, but remain surrounded by substantial amounts of gas left over from their formation and from subsequent mass loss. This material forms a complex mixture of relatively cool, dense clumps and more diffuse, warmer regions that respond to the varying radiation fields and winds from the massive stars. Closer to the stars, where the radiation intensity is highest, molecules are partly dissociated, and dust grains can be heated to temperatures where they emit strongly in the mid-infrared. Further out, shielded by intervening material, cooler gas persists and can serve as a site for ongoing low-mass star formation, or as a reservoir that will later be swept up by expanding shells. Within this wider HR5171 system, then the cool swollen star and the hot blue supergiant act together as a composite engine driving ionization fronts, heating dust and stirring the surrounding gas, even as each star follows its own evolutionary path. Less massive stars within the same region, some already on the main phase of their lives, and others still forming in the compressed ring, and embedded clumps orbit quietly in the combined gravitational potential of the molecular cloud and the central massive stars. The contrast between the cool extended envelope of V766 Centauri Aa and the compact hot atmosphere of HR5171b illustrates the range of possible outcomes for stars born with high initial masses in the same general environment. One has already cooled and swollen into a tenuous, unstable configuration near the empirical limits of stellar size, while the other remains relatively hot and compact, though still highly luminous. Together they exemplify how a small stellar group within a larger cloud complex can illuminate and reshape its surroundings, marking the place where massive star formation has reached some of its most dramatic and short-lived stages in this sector of the Centaurus arm. In star catalogues that list the brighter stars of the southern sky, the object now called V766 Centauri Aa first appears simply as one more luminous point in the constellation, Centaurus recorded with a visual brightness that places it at the limit of naked eye visibility under very dark conditions. Early photographic and photoelectric surveys measure its brightness and colour and classify it as a cool, highly luminous star of spectral type, around late G or early K, already marking it as a supergiant rather than an ordinary giant or main sequence star. At that stage, however, the distance to the star remains uncertain, and without a reliable distance its absolute luminosity and physical size cannot be firmly established. The star sits in a direction where interstellar dust is abundant, so its observed colour is strongly reddened and its apparent brightness is reduced. Astronomers recognise that any estimate of its intrinsic properties must correct for this reddening and dimming, but the amount of dust along the line of sight is itself not precisely known. As observations accumulate, it becomes clear that the star does not maintain a perfectly constant brightness. Repeated measurements over many seasons show changes in visual magnitude and colour index, sometimes modest, and sometimes more pronounced on timescales of hundreds of days and longer. Detailed light curves built from archives of observations reveal semi-regular variability, with intervals of relative stability interrupted by phases of deep fading and subsequent recovery. These patterns resemble the behavior of other rare, very luminous cool stars that occupy a region of the diagram, relating stellar brightness and temperature where massive stars evolve rapidly and unstably. On the basis of this photometric behavior and its spectral characteristics, the star is recognized as a member of the small class of yellow hypergiants, or cool S Doradus type variables, which are thought to represent a brief and unstable phase in the lives of very massive stars. Under this classification, the star is already notable, because yellow hypergiants are extremely rare in the Milky Way, and only a handful are known in nearby galaxies. Their rarity reflects both the high initial mass required and the short duration of the evolutionary stage. Long-term monitoring through the latter half of the 20th century and into the early 21st century shows that the star's variability is more complex than a single simple period. Analyses of the light curve identify several characteristic timescales, including intermediate periods of a year or two and longer-term trends over many years. Some intervals show relatively smooth low-amplitude pulsations, while others include deep minima where the visual brightness drops significantly, and the color becomes even redder. Infrared observations taken during these minima reveal that much of the missing visual light reappears at longer wavelengths, implying either cooling of the outer layers or increased absorption and re-emission by dust in the circumstellar environment. Together, these data suggest that the star's outer atmosphere and surrounding material undergo substantial structural changes over time. Parallel developments in infrared astronomy allow astronomers to construct a broad spectral energy distribution for the star, combining measurements from visible through mid-infrared wavelengths. When this distribution is corrected for estimated interstellar extinction, it reveals a total energy output hundreds of thousands of times greater than that of the Sun, even allowing for uncertainties in the distance and dust content. The luminosity required to match the observations places the star among the most powerful cool supergiants in the galaxy. From the luminosity and an estimated effective temperature of around 4,000 to 5,000 degrees, simple stellar models imply a radius many hundreds of times that of the Sun. These indirect estimates already hint that the star approaches the empirical upper limits of size, inferred for luminous supergiants. For many years, however, the lack of a direct measurement of the stellar disk leaves the exact radius uncertain. This changes when long baseline optical interferometry becomes available and is applied to the star. By combining the light collected by several widely separated telescopes, interferometers can measure extremely small angular sizes on the sky, sufficient to resolve the apparent disk of some of the largest and closest stars. When the star in Centaurus is observed with such an instrument, the data show that its angular diameter is surprisingly large for a yellow hypergiant at the estimated distance of several thousand parsecs. The resolved disk, even after allowing for the presence of an extended envelope, corresponds to a physical radius of order 1,000 solar radii or more, depending on the adopted distance and extinction. This places the object firmly within the group of the largest stars known comparable in radius to or exceeding famous red supergiants in other parts of the sky. Interferometric imaging also reveals that the brightness across the stellar disk is not uniform. The star shows an asymmetric shape with brighter and fainter regions, and appears to be surrounded by a fainter, more extended halo of emission. Some reconstructions suggest the presence of a somewhat smaller bright region, adjacent to the main disk, interpretable as a close companion star embedded within a shared envelope. Combined with the photometric evidence for regular variations on a timescale of several years, this leads to the proposal that the star is part of a contact or common envelope binary system, in which a lower mass companion orbits within the outer layers of the hypergiant. In this picture, orbital motion and mutual eclipses, together with changes in the extended envelope, contribute to the observed variability. Subsequent interferometric and spectroscopic studies refine this view, confirming the presence of complex structure and an extended environment, yet leaving some aspects of the binary interpretation open to debate. Some analyses argue that at least part of the apparent asymmetry and variability can be explained by large-scale pulsations and surface inhomogeneities in a star with extremely low surface gravity without requiring a fully embedded companion of the initially proposed type. At the same time, more precise astrometric measurements from space-based observatories provide improved though still not completely settled estimates of the distance. When combined with updated modelling of dust extinction, these suggest that the star may lie nearer than some early estimates implied, which would modestly reduce the inferred luminosity and radius. Even under the more conservative assumptions, however, the star remains extraordinarily large and luminous by normal stellar standards, with a radius of several hundred to around 1,000 times that of the Sun, and a luminosity of several 100,000 solar luminosities. It continues to rank among the largest and brightest cool stars known in the Milky Way. Through this sequence of observations and analyses, the object once catalogued simply as a bright southern supergiant gradually emerges as V766 Centauri Aa, an extreme hypergiant whose swollen envelope, heavy mass loss, and complex variability mark it as a stellar monster near the edge of known limits. Very massive stars in the Milky Way rarely live alone, and the system that hosts V766 Centauri Aa follows this pattern, presenting a layered architecture of companions and shared material rather than a single isolated object. At the centre lies the yellow hypergiant itself, the swollen, cool, and extremely luminous star whose extended envelope and complex brightness variations mark it as one of the most extreme objects of its type. Observations over many years show that its light does not vary in a purely random way. Instead, the brightness changes include features that repeat on a timescale of roughly a few years, with pairs of minima of slightly different depth and shape. This pattern resembles the eclipses seen in binary systems, where one star periodically passes in front of the other. When this photometric behavior is combined with interferometric images that resolve the apparent disk of the star, a picture emerges in which V766 Centauri Aa is not entirely alone at its core, but shares part of its extended outer layers with a smaller companion. Interferometric reconstructions show that the star's disk is not circular and uniform. The brightness appears uneven, with one region brighter than the rest, offset from the centre and changing position with time. Models that attempt to reproduce these data find that the simplest explanation is a close companion that orbits within or just at the edge of the hypergiant's distended atmosphere, producing a system in which both stars are immersed in a common envelope of gas. In such a configuration, the outer layers of the larger star overflow the region where its own gravity dominates, and material can move around both stars in a shared envelope that rotates roughly in step with the orbital motion. The close companion is estimated under this interpretation to be a luminous yellow star in its own right, but smaller and less massive than the hypergiant, with a radius perhaps around 1/3 that of the primary and a somewhat higher surface temperature. Its luminosity is a fraction of the primary's, yet still significant enough to contribute to the total energy output of the central system. The orbital period inferred from the repeating brightness pattern is of order 1,300 days, meaning that the companion circles the primary at a distance comparable to several times the radius of the hypergiant itself. In a more ordinary system, This would allow each star to retain a distinct atmosphere, but the extreme size of V766 Centauri Aa means that its outer layers already extend well into the orbital separation, and the companion does not orbit in empty space but moves through the dense, slowly outflowing gas. The shared envelope and the close proximity make the system an example of strong binary interaction among very massive stars, a phase thought to be brief and dynamically complex. The close pair's structure, and even its basic parameters, however, are not completely settled. Later interferometric studies and updated distance estimates introduce some tension with the earliest common envelope model. Some analyses suggest that part of the apparent asymmetry and brightness variation may be due to large convective cells and pulsations in the hypergiant's own envelope, which can produce bright and dark patches across the stellar disk, as well as changes in radius and effective temperature over time. In this view, a companion may still be present, but its properties and degree of contact with the envelope become less certain, and the system might not be as deeply in a common envelope phase as initially proposed. The current understanding is that the central star almost certainly does not have a perfectly symmetrical isolated atmosphere, and that additional structure, whether due to a close orbiting companion to giant surface cells or to both, plays a major role in shaping its observed appearance and variability. The secure elements are that V766 Centauri Aa is a hypergiant with very low surface gravity, that its envelope is extended and unstable, and that there is strong evidence for a secondary source of light very close to the main disk. The exact mass of the companion, the degree to which it shares the envelope, and the precise elements of the orbit remain active topics of study. Surrounding this central pair or central complex lies a second level of architecture in the form of a more distant hot supergiant companion, commonly designated as HR 5171b. On the sky, this star sits only a few arcseconds from the hypergiant. Yet at the distance of the system, this small angle translates into a projected separation of tens of thousands of astronomical units. HR 517. 1b displays a spectrum typical of an early type blue supergiant with a high effective temperature and very strong luminosity, much of it emitted in the ultraviolet. Even though it appears several magnitudes fainter than the yellow hypergiant at visible wavelengths, this is partly because its radiation is shifted into shorter wavelengths that are more heavily absorbed by dust, and partly because both stars suffer heavy reddening along the line of sight. When their total energy outputs are reconstructed from multi-wavelength data and corrected for extinction, the blue star proves to be a very luminous object in its own right, comparable in overall power to the hypergiant, though differing in temperature and radius. The spatial and kinematic evidence indicates that HR 5171b is associated with the same evolved nebula and molecular cloud complex as V766 Centauri Aa. The velocities of the stars along the line of sight match those of the surrounding gas, and their positions coincide with the center of the GUM-48d region, where the ionized ring and its parent cloud were carved by earlier massive stars. This makes it likely that HR 5171b and V766 Centauri Aa are part of the same small stellar group and share a common origin in the same star-forming event, even if their wide projected separation and uncertain true separation leave open the question of whether they form a gravitationally bound pair over long times. At such large separations, the orbital period would be very long, and the gravitational influence of the wider galactic environment and the parent cloud could perturb or disrupt any bound orbit over millions of years. Even if the two are only loosely bound, however, their combined radiation has been sufficient to clear and ionize the cavity, that now appears as the evolved nebula. In architectural terms, the HR 5171 system can be viewed as a hierarchical multiple. At the innermost scale, the hypergiant and its close companion, whether fully in a common envelope phase or in a slightly looser but still interacting configuration, form a tight pair whose evolution is dominated by internal mass transfer tidal forces and the dynamics of an extended unstable atmosphere. At the next scale, this pair and the distant blue supergiant form a wider grouping that shares a common birth environment and contributes collectively to the shaping of the nebula and molecular cloud. Beyond that, the system is embedded within a loose association of less massive stars and embedded young objects that populate the interior of the cavity and the compressed ring at its edge. The architecture is not as regular as the neat nested orbits sometimes drawn for idealized multiple stars, but the hierarchical view helps to organize the different levels of interaction. The strongest gravitational coupling occurs within the central pair, where the companion moves through the hypergiant's extended atmosphere and likely influences its mass loss. The most significant radiative influence on the nebula as a whole arises from the combined output of the hypergiant and the blue supergiant, whose ultraviolet and visible light have ionized and heated the gas over millions of years. The lower mass stars, while numerous, add only modestly to these energy budgets. Uncertainties remain at each of these levels. The exact configuration of the close pair is still being refined as new interferometric and spectroscopic data arrive. The physical association of the blue supergiant with the hypergiant, while strongly suggested by current measurements, could be revised if future parallaxes or velocity studies point to a somewhat different distance or motion. Despite these open questions, the overall picture is clear enough to support the idea that V766 Centauri Aa resides not in isolation, but in a small complex system where multiple massive stars and an intricate envelope of gas act together. This stellar architecture sets the stage for understanding how the extended circumstellar environment has been built and maintained, and how material moves between the central stars and the surrounding nebula in the present epoch. Around V766 Centauri Aa, the space between the star and the wider nebula does not lie empty. Instead, it is filled with an extended circumstellar envelope, a region of gas and dust that the star itself has shed over time. A circumstellar envelope is the material surrounding a star that has been lost from its outer layers through winds or eruptions, and in this case that material forms a thick irregular shell that blends gradually into the broader gas and dust of the GUM-48D complex. Close to the star, the envelope is dominated by dense gas flowing outward at relatively low speeds for a stellar wind a few tens of kilometers per second, rather than the hundreds or thousands found around hotter, more compact stars. This slow outflow, driven by the combined action of radiation from the star and the low gravity at its extended surface, allows material to linger near the star for a long time before it drifts into the wider nebula. As the gas moves outward, conditions in the cooling flow favor the formation of dust grains. Elements such as oxygen, silicon, magnesium, and iron supplied by the star's atmosphere condense into solid particles when the temperature drops below the threshold at which they can remain in gaseous form. These grains gather first in the inner parts of the wind at distances where the radiation field is still strong, but no longer hot enough to destroy the solids. Further out, they become more abundant and begin to dominate the envelope's interaction with starlight, absorbing and scattering radiation from the star and re-emitting it at longer wavelengths. The result is a layered structure in which gas and dust are intertwined but not uniformly distributed. Observations across the spectrum indicate that the circumstellar envelope is dense and rich in dust, compared with those around many other luminous stars. The star's spectral energy distribution shows a strong excess of emission at infrared wavelengths, above what would be expected from the photosphere alone. This excess arises because dust grains in the envelope absorb visible and ultraviolet light from the star and re-radiate that energy as heat in the infrared. At the same time, the visible light that escapes directly from the star to a distant observer has passed through both the interstellar dust in the molecular cloud and the circumstellar dust close to the star. Each layer dims and reddens the light by preferentially removing shorter wavelengths, so that by the time it arrives at telescopes the light is far redder than it was when it left the stellar surface. Correcting for this combined extinction is one of the main challenges in determining the true properties of V766 Centauri Aa. Some of the reddening can be attributed to the general dust content of the Centaurus arm and the parent molecular cloud, which also affects other stars in the region. However, comparisons among stars that share the same line of sight show that the hypergiant suffers additional reddening beyond that common background. This excess is naturally explained by dust in its own envelope, which lies close to the star and only affects light coming from the hypergiant itself. Infrared images and interferometric data support this interpretation by revealing a halo of emission around the stellar disk extending to angular scales larger than would be expected from the photosphere alone. Within this halo, the brightness falls off gradually with distance from the center, indicating that the dust density decreases outward, but remains significant over distances many times the radius of the star. The geometry of the envelope is complex rather than perfectly spherical. High-resolution observations suggest asymmetries such as brighter arcs or clumps in certain directions and possible flattening or elongation of the dust distribution. These features could arise from several processes. The slow outflow may be channeled or disturbed by the presence of the close companion, moving within or near the extended atmosphere, creating preferred directions for mass loss and producing regions of enhanced density where streams of gas and dust meet or overlap. Large convective cells at the surface of the hypergiant where rising and sinking gas carry heat and material outward can also lead to uneven ejection of matter, with some sectors of the stellar surface contributing more to the wind than others. Over time, these anisotropies are carried outward by the flow imprinting an irregular structure on the envelope. Evidence for episodic mass loss is found in the way the brightness and colour of the star change during the deeper minima in the light curve. During some fading events, the visual brightness drops sharply, while the infrared emission increases or remains strong, implying that additional dust has formed or moved into the line of sight. In other intervals, the star becomes cooler and larger while maintaining a similar total luminosity, consistent with changes in the outer layers rather than in the core energy supply. These behaviors suggest that the circumstellar envelope is not built solely by a steady unchanging wind, but also by episodes in which mass loss temporarily increases, perhaps in response to pulsations or structural adjustments in the extended atmosphere. Each episode adds a new shell or layer of gas and dust to the envelope, which then drifts outward and merges gradually with older material. Over hundreds or thousands of years, such episodes can build a substantial circumstellar shell containing a significant fraction of the star's outer layers. The composition and grain sizes in the dust shell affect how it interacts with light. In an oxygen-rich environment such as that expected around a massive yellow hypergiant dust, tends to form in the form of silicate grains and related compounds. These grains have characteristic features in the mid-infrared broad bands of emission that rise above the continuum. Observations of similar stars show such signatures, and while individual measurements for V766 Centauri Aa carry uncertainties due to blending with the broader nebular emission and heavy interstellar extinction, The general behavior indicates that its dust shell likely follows this pattern. The grains are not all the same size. Smaller grains scatter light more effectively at shorter wavelengths, enhancing the reddening and creating a diffuse halo of scattered light around the star, while larger grains contribute more to the smooth thermal emission in the infrared. The mix of grain sizes within the envelope thus helps set the exact shape of the spectral energy distribution and the appearance of the surrounding halo. At larger distances from the star, the circumstellar envelope shades into the wider nebula. Gas and dust lost by V766 Centauri Aa slow down and mix with the material already present in the GUM-48d region, adding chemically enriched matter to the local interstellar medium. Elements synthesized in the interior of the star and brought to the surface by convection are carried outward in the wind and eventually incorporated into new dust grains or dispersed as gas. In this way, the envelope serves as a bridge between the star and its environment, mediating the exchange of mass and energy. The same outflow that builds the circumstellar shell also contributes to the filaments and clumps seen in the interior of the evolved cavity, though disentangling the specific contributions of this star from those of other massive stars and earlier evolutionary phases is difficult. For an external observer, the most immediate effect of the envelope is its reshaping of the star's observed light. The star appears redder and often fainter than it would without the circumstellar dust, and its brightness changes reflect not only internal pulsations, but also changes in the distribution and properties of the dust along the line of sight. In some phases, parts of the envelope may become more transparent, revealing closer to the intrinsic color of the extended atmosphere. In others, newly formed dust or denser clumps can obscure more of the star, shifting the balance of energy toward the infrared. Through all of these changes, the slow outflows continue to carry matter away from the star building and replenishing the dusty shell that both hides and reveals the underlying hypergiant. The circumstellar envelope around V766 Centauri Aa is therefore not a static shell, but a dynamic layered structure formed by past and ongoing mass loss. It blurs the boundary between star and nebula, provides a record of the star's recent history, and sets the conditions under which the outer atmosphere and apparent surface are observed, linking the extended environment directly to the measurements that define this object as a stellar giant near the limits of known size and luminosity. From the viewpoint of a distant observer, the point at which a star appears to end and surrounding space begins is not a hard physical boundary, but the place in the atmosphere where the gas becomes transparent enough for most of the light to escape. This apparent surface, called the photosphere, is defined not by a solid layer, but by a gradual transition from opaque to transparent gas. In ordinary stars like the Sun, this transition occurs over a relatively narrow range of heights, so the photosphere can be treated as a thin shell with a well-defined radius. In a star as swollen and luminous as V766 Centauri Aa, the situation is different. The outer layers are so extended and tenuous that the density falls off slowly with distance, and the combination of gas and dust in the outflowing wind spreads the region where light last interacts with matter over a large radial range. Instead of a sharp photosphere, the star presents a pseudo-photosphere, an extended volume in which different wavelengths of light originate at different depths. At some wavelengths, the optical depth, the measure of how strongly the gas and dust absorb and scatter, light reaches a value near 1 at a radius close to what would be considered the stellar surface in a more compact star. At others, especially where molecular absorption or dust opacity is strong, the optical depth of 1 is reached farther out in layers that belong more to the circumstellar envelope than to the underlying hydrostatic atmosphere. The result is that the apparent radius of the star depends on the wavelength and on the structure of the outer layers. interferometric measurements make this effect visible. By combining the light from several telescopes separated by distances of tens to hundreds of meters, astronomers effectively create a virtual telescope with a very large aperture capable of resolving tiny angles on the sky. When they observe V766 Centauri Aa at different wavelengths, they find that the angular diameter inferred from the data changes with wavelength and does not correspond to a single uniform disk. In some spectral bands, particularly in the near-infrared, the star appears larger than in others, indicating that the dominant emission arises from higher, cooler layers in the atmosphere or from the inner parts of the dusty wind. In addition, the brightness across the resolved disk does not fall smoothly from the center to the edge in the simple pattern known as limb darkening, which describes how the outer parts of a stellar disk appear dimmer than the center, because the line of sight passes through cooler layers. Instead, the disk of V766 Centauri Aa shows irregularities with brighter and darker patches that change over time. These patches suggest that the pseudo-photosphere is shaped by large convective cells and by inhomogeneities in the dust and gas distribution, rather than being a smooth symmetric shell. In regions where warm gas and dust are denser, the optical depth at a given wavelength becomes larger, so the effective surface from which that wavelength escapes moves outward and may appear slightly cooler and dimmer. In regions where the density is lower, or where the line of sight encounters fewer absorbing particles, the light can emerge from somewhat deeper, hotter layers, producing brighter zones on the disk. Because the outer atmosphere is unstable and subject to pulsations, these structures evolve on timescales of months to years, contributing to the complex variability observed in the star's brightness and color. The pseudo-photosphere is also influenced by the slow wind that carries material away from the star. As the wind accelerates outward, it remains optically thick at some wavelengths, over a considerable radial range, effectively extending the photospheric region into the outflow. This means that part of what is seen as the stellar surface may in fact be radiation emerging from layers already in motion, rather than from gas that still participates in a quasi-static atmosphere. In extreme cases, when the mass loss rate is especially high, the pseudo-photosphere can form almost entirely in the wind, hiding the true hydrostatic radius of the star inside a shroud of moving gas. For V766 Centauri Aa, the available data suggest a mixed regime in which both a very extended atmosphere and a dense wind contribute to the observed surface, with the balance shifting as the star goes through phases of stronger or weaker mass loss. The presence of a close companion moving within or near the extended envelope adds further complexity. The orbiting star can locally disturb the density and velocity field in the outer layers, carving out slightly lower density corridors or compressing gas along its path. These perturbations can alter the shape of the pseudo-photosphere, creating asymmetries that may appear as elongations or bright spots in interferometric images. Over the course of the orbital period, these structures move and change, superposed on the slower evolution, driven by pulsations and long-term structural adjustments in the hypergiant's envelope. For an external observer, all of these effects combine to produce a stellar disk that is large, irregular, and dependent on wavelength. The apparent radius inferred from one set of observations may differ noticeably from that derived at another time or in another spectral band, not because the underlying core of the star has changed dramatically on those timescales, but because the outer layers that define the pseudo-photosphere have shifted in density, temperature, and composition. During phases when the star undergoes cooling episodes associated with increased mass loss or dust formation, the pseudo-photosphere can move outward, the effective temperature decreases, and the star appears redder and larger in angular size. During phases when the atmosphere becomes more compact and the mass loss slows, the effective surface can move inward, raising the apparent temperature and shrinking the angular diameter. These changes are gradual on human timescales, but significant when integrated over years and decades of monitoring. They reflect the delicate balance between gravity, radiation pressure, and gas dynamics in the outer layers of a star operating close to the empirical limits of luminosity for its mass. The concept of a pseudo-photosphere is therefore more than a technical refinement. It captures the fact that in V766 Centauri Aa there is no single simple surface. Instead, there is a thick dynamic zone where photons last interact with matter before escaping to space, and the shape and location of this zone depend on wavelength, time, and direction. Interpreting observations of such a star requires careful modelling that accounts for this extended wavelength-dependent surface, so that derived quantities like radius, temperature, and luminosity are understood as averages over a complex three-dimensional structure rather than as properties of a sharp boundary. In the case of V766 Centauri Aa, these models confirm that even when allowance is made for the pseudo-photosphere, the characteristic radius remains enormous and the luminosity remains extremely high, reinforcing the classification of this object as one of the most inflated and radiant stars known in the Milky Way, with an observable surface that is as much a property of its unstable atmosphere and wind as of its deeper interior. In any very luminous star, the light emerging from the hot interior does more than simply shine into space. It exerts a gentle but persistent push on the outer layers. In V766 Centauri Aa, where the luminosity climbs to several 100,000 times that of the Sun, and the surface gravity is very low because the outer layers are spread over a radius of many hundreds of solar radii, this radiative push becomes strong enough to drive a continuous outflow of gas. This outflow is the stellar wind, a stream of material that leaves the star and carries away mass momentum and energy. In hot, compact stars, winds can move at thousands of kilometers per second and remain relatively tenuous. In a swollen hypergiant like V766 Centauri Aa, the wind is slower and denser, with characteristic speeds of a few tens of kilometers per second, yet with so much material flowing outward that over astronomical times a significant fraction of the star's envelope can be lost. Spectroscopic observations encode this outflow in the shapes of spectral lines. Some lines show profiles with a bright emission component, accompanied by a blue-shifted absorption trough, a pattern known as a P Cygni type profile that signals gas flowing outward along the line of sight and absorbing light from deeper layers. Other lines broaden and shift as the wind accelerates away from the star. By modelling these features with radiative transfer calculations, astronomers infer the wind's velocity structure and density. For V766 Centauri Aa, these models indicate a dense, slow wind with mass loss rates large enough to alter the structure of the outer envelope over the lifetime of the hypergiant phase. The outflow does not consist of pure gas. As the material moves away from the warm pseudo-photosphere described previously, it cools. At certain distances from the star where the temperature drops below a few thousand degrees, conditions favour the condensation of dust grains out of the gas. These grains form around tiny seeds picking up atoms of silicon oxygen, magnesium iron, and other elements to build silicate and related compounds. Once formed, the grains interact strongly with radiation, absorbing and scattering visible and ultraviolet photons, and re-emitting the absorbed energy as infrared light. Radiation pressure on dust grains is very efficient, so the presence of dust in the wind increases the outward acceleration. The grains feel a strong push from the stellar radiation, and drag the surrounding gas with them, through collisions coupling the gas and dust into a single outflowing fluid. In this way, the wind in V766 Centauri Aa likely operates in a hybrid regime, partly driven by direct radiation on gas in the inner layers and partly by radiation on dust in the outer layers. The mass loss is not perfectly steady. The variability seen in the light curve, especially during deep minima, when the visual brightness decreases and the infrared emission strengthens, indicates episodes when the mass loss rate and dust formation increase. During these episodes, more material is propelled into the wind, and a denser shell of gas and dust builds up at radii, where the temperature favours grain growth. Between such episodes, the mass loss may drop to a lower level, adding only a thinner layer of material. Over time, the wind therefore develops a stratified structure, with shells and arcs of enhanced density embedded in a more nearly continuous outflow. In V766 Centauri Aa, the presence of a close companion moving within or near the extended envelope adds another layer of complexity. When a massive star expands to the point that its outer layers reach or exceed the region where its own gravity dominates over that of a companion, the configuration approaches what is called Roche lobe overflow. The Roche lobe is the teardrop-shaped region around each star in a binary system within which material remains gravitationally bound to that star. If the hypergiant's envelope extends to this region, gas can move toward the inner point between the stars, and some of it can flow into the gravitational sphere of the companion. In a common envelope phase, much of the outer gas does not belong cleanly to one star or the other, but instead fills a shared volume around both. For V766 Centauri Aa's interferometric evidence for a secondary source embedded close to the bright disk, and for asymmetric brightness structures supports the idea that at least parts of the envelope may behave in this way. In such a situation, mass loss is not simply a radial wind flowing away from a single star. Near the orbital plane, gas can stream from the hypergiant toward the companion through the inner Lagrange region, forming a flow that spirals around both stars. Friction and drag in this common envelope can transfer orbital energy from the motion of the stars into the gas heating it and helping to lift it outward. Some of this gas may eventually escape the system, entirely carrying away angular momentum and contributing to the large-scale circumstellar envelope and the interior of the evolved nebula. Some may settle into structures such as circumbinary disks or toroidal accumulations in the equatorial plane, depending on how the flow balances rotation, radiation, pressure, and gravity. Observationally, the detailed geometry of these flows in V766 Centauri Aa is not fully mapped, because the angular scales are tiny and the structures are faint compared with the bright central source. However, clues appear in the way spectral lines vary with time and in the wavelength-dependent asymmetries seen in interferometric images. Changes in the strengths and shapes of wind-sensitive lines suggest that the mass loss is not uniform in all directions, and that some directions possibly aligned with the orbital plane experience enhanced flows. Subtle shifts in the apparent center of light and in the elongation of the resolved disk repeating on timescales comparable to the proposed orbital period hint at moving structures in the envelope. Taken together, these indications point to a situation in which the wind and mass loss are strongly influenced by binary interaction, even if the exact configuration remains under study. Beyond the immediate region of the common envelope, the stellar winds from V766 Centauri Aa and from the more distant blue supergiant companion interact with the gas inside the cavity of GUM-48d. The hypergiant's wind is slow and dense, rich in dust, and carries a substantial mass flux. The blue supergiant's wind is faster and more tenuous, driven by its hotter, more compact atmosphere, and carries more momentum per unit mass. Where these winds meet, they form a colliding wind region, a zone where gas from each star decelerates in shocks, heats, and then cools by radiating energy. In other massive binaries, such regions can produce characteristic X-ray emission and sculpt the surrounding dust into arcs and spiral patterns. For the V766 Centauri Aa system, the limited observations available suggest that some form of interaction between winds is present, although the exact morphology is not as clearly imaged as in closer or less heavily reddened systems. The density and slow speed of the hypergiant's wind imply that it provides a substantial background medium into which the blue supergiant's faster wind plows, creating a cavity or bow-shaped zone around the hotter star, and possibly compressing dust into ridges or shells on larger scales. Within a few hundred stellar radii of V766 Centauri Aa, the flow transitions from the quasi-hydrostatic outer atmosphere and pseudo-photosphere into the accelerating wind. In this zone, gravity, radiation pressure, gas pressure, and turbulent motions all contribute to the dynamics. The gas gradually picks up speed as the radiative force overcomes gravity, starting from very low velocities near the sonic point where the flow becomes supersonic and rising toward the terminal velocity of the wind. Dust formation begins in this region for those portions of the flow that remain sufficiently dense and cool, and once grains appear, the acceleration increases. Any perturbations from pulsations or from the gravitational pull of the companion can change the density and temperature structure in this critical region, leading to localized enhancements in mass loss and in dust production. These enhancements then propagate outward as clumps or arcs embedded in the wider wind. The long-term effect of this continuous and episodic mass loss is a steady reduction in the mass of the envelope surrounding the core of V766 Centauri Aa. The star responds by adjusting its structure, which feeds back on the wind through changes in luminosity radius and effective temperature. The immediate observable outcome is the extended dusty envelope and complex pseudo-photosphere described previously, but the ongoing removal of mass is also an integral part of the star's evolutionary path. In the present moment, the wind's mass loss and possible common envelope flows around V766 Centauri Aa form a dynamic interface between the hypergiant and its environment, redistributing material within the system and supplying the gas and dust that blend into the interior of the evolved nebula. The details of these flows, their geometry and their time dependence remain subjects of active investigation, yet even with the current uncertainties, the overall picture is one of an extreme star operating near the edge of radiative balance, shedding its outer layers through dense structured winds and complex binary-driven outflows that link its extended atmosphere directly to the surrounding interstellar medium. The brightness of V766 Centauri Aa, when followed patiently over many years, does not trace a simple repetitive pattern, but instead shows a layered mixture of short-term pulsations, medium-term cycles, and longer secular drifts that together reveal a restless outer atmosphere close to instability. Photometric records collected in visible light over decades display variations on timescales of months to a few years, with amplitudes that range from modest undulations to deep minima in which the star fades by more than a magnitude and then slowly recovers. Superposed on these larger swings are smaller quasi-periodic fluctuations that repeat on shorter timescales, sometimes emerging clearly for a few cycles before fading back into a more irregular background. When observers examine the brightness in more than one color, they find that the star generally becomes redder as it fades in visible light and bluer as it brightens, a behavior consistent with changes in effective temperature and with increased absorption by dust during some of the deeper minima. At the same time, infrared measurements show that the total energy output changes less dramatically than the visible brightness alone would suggest. During some of the deepest fades, the infrared flux actually increases or remains approximately steady, indicating that a larger fraction of the stellar radiation is being intercepted and re-emitted by dust in the circumstellar envelope. Taken together, these patterns show that the variability arises from a combination of atmospheric pulsations and changes in the distribution and opacity of the surrounding dust, rather than from large fluctuations in the core nuclear energy supply. Spectroscopic monitoring provides a complementary view. At phases when the star appears relatively bright, and its color indices indicate a somewhat warmer state, the spectrum resembles that of an extremely luminous late G or early K supergiant, with strong absorption features from neutral metals and some molecular bands broadened by macro-turbulence and by the extended nature of the atmosphere. During cooler, fainter phases, the spectrum shifts toward later types with deeper molecular bands and changes in line strengths that imply a lower effective temperature and often a larger radius. Radial velocity measurements, which track the small shifts in line positions as the outer layers move toward or away from the observer, reveal patterns consistent with radial pulsations, where the atmosphere expands and contracts more or less coherently. In some intervals, these pulsations appear roughly periodic with characteristic timescales of hundreds of days. In others, the pattern becomes more irregular, suggesting the simultaneous presence of several pulsation modes with slightly different periods and amplitudes. Line profile variations give further clues. Some lines associated with the dense wind show Persigny-type shapes that change with time, indicating that the velocity and density structure of the outflow vary as the atmosphere breathes in and out. In addition, subtle asymmetries and moving subfeatures in photospheric lines point to large-scale convective cells or inhomogeneities that drift across the projected disk. When interferometric images are available for different epochs, they show that the brightness distribution across the stellar disk changes, over time confirming that the surface is not uniform and that bright and dark regions evolve in concert with the photometric and spectroscopic variations. The connection between brightness changes and atmospheric structure becomes especially clear during episodes when V766 Centauri Aa undergoes a deep visual dimming. In these phases, the spectral type shifts to cooler values. The apparent angular diameter measured in the infrared tends to increase, and line profiles indicate slower outflow velocities near the base of the wind, all consistent with an expanded cooler atmosphere. At the same time, the infrared excess grows stronger, and mid-infrared observations reveal enhanced dust emission. One interpretation supported by similar behavior in other yellow hypergiants is that during these episodes the outer layers of the star expand cool and condense dust more efficiently, leading to both an increase in radius and an increase in circumstellar obscuration. Once the episode passes, the atmosphere contracts somewhat, the effective temperature rises, and the newly formed dust moves outward, reducing its effect on the line of sight. Thus, the light curve records both the mechanical response of the atmosphere to internal instabilities and the radiative effects of dust production and transport. Not all variability is tied to such dramatic events. Even in relatively quiet intervals, small amplitude changes persist with timescales that suggest low-order radial pulsations and possible non-radial modes. In a very luminous star with an extended envelope and low surface gravity, such pulsations are expected. The outer layers are only weakly bound, and small changes in the balance between radiation pressure and gravity can send waves propagating through the envelope. These waves can steepen into shocks, temporarily compressing or rarefying the gas and altering the local opacity. In regions where opacity increases, radiation becomes more trapped, heating the gas and leading to expansion. Where opacity decreases, radiation escapes more easily, cooling the gas and promoting contraction. This cycle can sustain oscillations that modulate the stellar radius and temperature. Because V766 Centauri Aa lies in a region of the diagram relating luminosity and temperature, where theoretical models predict dynamical and thermal instabilities, sometimes referred to as a stability border. For very luminous, cool stars, its envelope is particularly prone to such behavior. The presence of the close companion and the complex wind structure adds further subtlety. As the companion moves through or near the extended atmosphere, its gravity perturbs the local density and velocity field, potentially seeding or enhancing certain pulsation modes. If the orbit and the intrinsic pulsation periods are commensurate, beat patterns can arise in the light curve, producing cycles that only approximate a regular period over a few years before drifting. Some analyses of the long-term photometric data suggest that the deepest minima and largest expansions in radius cluster around specific phases of the proposed orbital cycle, hinting that binary interaction may help trigger or at least modulate the most extreme instability episodes. However, the data are not yet sufficient to establish a firm, causal link, and alternative explanations based purely on atmospheric dynamics remain viable. Uncertainties in the distance and extinction also complicate the conversion of observed flux changes into absolute luminosity variations, though the broad conclusion that the total energy output remains relatively stable while radius and temperature shift is robust. The pattern of brightness and spectral changes in V766 Centauri Aa shares characteristics with other extremely luminous unstable stars that skirt the limits of radiative stability. Like some famous examples among yellow hypergiants and related variable stars, it shows a combination of semi-regular pulsations, occasional deep dimming events, and persistent line profile variations, indicative of a dynamic atmosphere and wind. Yet the details of its behavior, including the timescales, amplitudes, and degree of dust involvement, are specific to its mass composition, environment, and binary architecture. Long-term monitoring continues to refine the picture, making it clear that the star rarely, if ever, settles into a truly steady state. Instead, its outer layers seem to adjust continually, seeking a quasi-equilibrium that remains marginally stable at best. Each expansion and contraction, each episode of enhanced dust formation, and each modulation in the wind reflects slight shifts in the underlying balance of forces in a star operating close to the empirical upper boundaries of size and luminosity. For a distant observer collecting light curve points and spectra over years and decades, this manifests as a slowly unfolding record of atmospheric instabilities in real time, written in the subtle and not so subtle fluctuations of a single luminous point embedded deep within the Centaurus arm. Beneath the pseudo-photosphere of V766 Centauri Aa, the outer envelope extends inward through layers where the gas is still relatively cool and tenuous by stellar standards, but already far denser and hotter than the material in the circumstellar wind. In these layers, energy generated deep in the interior must work its way outward through a medium that is only marginally stable against the combined effects of gravity and radiation. The luminosity of the star is so high that the outward thrust of light on the gas comes close to matching the inward pull of gravity across much of the envelope. In regions where the gas becomes more opaque, meaning that it absorbs and scatters light more strongly, the local ratio of radiative force to gravity approaches unity, and the material finds itself in a delicate balance. Small changes in temperature, density, or composition can tip this balance and set large volumes of gas in motion. The opacity of the gas in the outer envelope is not fixed. It depends on which atoms and ions are present, on the degree to which hydrogen and helium are ionized, and on the local temperature and density. In cool, extended outer layers, partial ionization of hydrogen and helium plays a central role. At certain temperatures, hydrogen is partly ionized so that some electrons remain bound while others are free. In this range, adding heat does not immediately raise the temperature very much, because much of the energy goes into breaking atomic bonds, rather than into increasing the random motions of particles. As a result, the gas becomes more compressible, and its opacity can increase sharply. A similar behavior occurs where helium changes from a neutral state to a singly ionized state, and again where it becomes doubly ionized at somewhat higher temperatures. These partial ionization zones act as regulators and amplifiers in the envelope. When a layer in such a zone is compressed, its temperature rises, more ionization occurs, and the opacity increases. Higher opacity traps radiation more effectively, raising the pressure and pushing the gas outward. As the layer expands, it cools, recombination reduces the opacity, radiation leaks out more easily, and the pressure support weakens, allowing gravity to draw the gas inward again. This cycle of compression and expansion can sustain pulsations and contribute to the unstable behavior of the outer envelope. In more modest stars, these partial ionization-driven processes produce familiar variable stars with periodic brightness changes. In a hypergiant like V766 Centauri Aa, the vast scale of the envelope and the proximity of the luminosity to the limit where radiation and gravity nearly balance make the response more dramatic. Convective motions also play a major role in transporting energy through the outer envelope. Convection occurs when gas becomes buoyantly unstable, with hot, less dense material rising and cooler, denser material sinking. In regions where the temperature gradient required to carry the luminosity outward by radiation alone would exceed a certain critical value, the gas reorganizes into convective cells that carry heat mechanically. In V766, Centauri Aa models of very luminous, cool stars indicate that large portions of the envelope are convectively unstable. Giant convective cells, each occupying a significant fraction of the stellar surface, rise and fall on timescales of months to years, stirring the envelope and bringing processed material from deeper layers closer to the surface. These motions alter the local density and temperature structure, contributing to the inhomogeneities seen in interferometric images and to the irregularities in the wind, because convection in such an extended low-gravity envelope is turbulent, and three-dimensional. It does not settle into a simple pattern. Instead, rising plumes and sinking downdrafts interact, merge and decay, creating a constantly shifting patchwork of hotter and cooler regions. In zones where rising material reaches the outer layers, the extra heat can puff up the atmosphere locally, lifting the effective surface outward and lowering the local gravity even further. In zones where cooler material sinks, the layers above may contract slightly. The combined effect is a surface that is not only bright and dark in patches, but also slightly corrugated in radius, with some regions protruding farther than others into the circumstellar envelope. This corrugation affects where the optical depth equals unity at each wavelength, so the pseudo-photosphere acquires the irregular shape inferred from high-resolution observations. Deeper in the envelope, at temperatures of many tens of thousands of degrees, additional opacity peaks appear due to heavier elements, including contributions from iron group ions. These opacity peaks can further impede the flow of radiation and contribute to the inflation of the envelope, though they lie below the layers where dust forms and where the pseudo-photosphere resides. Their presence means that a significant fraction of the envelope is supported by radiation, passing through zones of enhanced opacity making the overall structure more extended than it would be if the opacity were lower and smoother. The energy generated in the core must traverse these layers, and the difficulty of doing so manifests as a large radius and low surface gravity. The combined action of partial ionization, convection, and opacity peaks brings parts of the envelope close to the threshold where the outward radiative force matches gravity. Where this threshold is nearly reached, even a small fluctuation can drive matter outward. A slight increase in luminosity or opacity can momentarily tip the balance in favor of outward acceleration, allowing layers to drift away and join the stellar wind. Conversely, a slight decrease allows gravity to reassert control, pulling material back toward the deeper regions. In a star as luminous as V766 Centauri Aa, with a mass that has been reduced by prior mass loss, this threshold lies not only at the very surface but throughout substantial parts of the outer envelope. The result is a structure in which many layers hover near marginal stability, never fully relaxed. These layers also feel the influence of rotation and of any non-radial motions. Even if the star rotates slowly compared with more compact massive stars, the vast radius means that modest rotation rates translate into significant linear speeds at the equator. Centrifugal forces slightly reduce the effective gravity in equatorial regions, making it easier for radiation to push material outward there. Convection and pulsations can accentuate this effect, locally producing preferred directions for mass loss. Over time, such directional biases can imprint asymmetries on the envelope, leading to more extended structures or higher densities in some latitudes than in others. The presence of a close companion can further perturb the outer envelope. In the hemisphere facing the companion, tidal forces raise a slight bulge, altering the local gravity and potentially the convective pattern. Gas in these regions may find it easier to overflow the equipotential surface, connecting the two stars, feeding the shared envelope, or streaming toward the companion. The energy carried outward by radiation and convection must then navigate a geometry that is no longer spherically symmetric, and the stress on the envelope can become concentrated in particular sectors. Under these conditions, episodes of enhanced mass loss can begin with localized disturbances in the outer layers that grow and spread, rather than with global perfectly symmetric expansions. From the perspective of stellar structure theory, the outer envelope of V766 Centauri Aa represents an extreme case of a luminous low-gravity envelope with strong opacity variations. Models that attempt to reproduce its properties show that small changes in parameters such as mass composition or mixing length, a measure of convective efficiency, can lead to different envelope extents and stability properties. Some models find that for certain combinations, the envelope naturally inflates to a radius comparable to that inferred from observations, with the outer layers becoming very loosely bound. Others indicate that slight increases in luminosity or decreases in mass could push the envelope into a regime where large-scale outbursts become more likely. While the exact parameters of V766 Centauri Aa remain uncertain due to distance and extinction, the general conclusion is that its outer envelope occupies a narrow band of solutions in which energy transport is difficult, and the star hovers near structural limits. In the present moment, this configuration manifests as a thick, convective, partially ionized envelope through which energy struggles to escape. Radiation pushes upward against gravity in regions where opacity is high. Convection carries heat in giant cells that roil the surface. Partial ionization zones act as valves that open and close in response to compression and expansion. Gas in these layers is both the source of the dense wind and the arena where pulsations and local instabilities are born. Each photon emerging from the deeper interior must thread its way through this complex medium before it reaches the pseudo-photosphere and finally escapes into space. Each parcel of gas in the envelope feels forces that are finely balanced, yet subject to continual perturbation. The structure and behavior of this outer envelope therefore link directly to the observed brightness changes, to the mass loss that builds the circumstellar shell, and to the classification of V766 Centauri Aa as a star whose size and luminosity press against the outer bounds of what a stable envelope can support. Deep inside V766 Centauri Aa, far beneath the convective partially ionized outer envelope, the conditions change from loosely bound marginally stable layers to a compact intensely hot interior where nuclear reactions proceed in multiple shells. Direct observations cannot reach these depths because photons that escape from the core must scatter countless times through the dense inner regions and through the extended envelope before they emerge at the pseudo-photosphere. Instead, the structure of the interior is inferred from models of very massive stars that share similar luminosity, surface temperature, and chemical signatures with V766 Centauri Aa. These models describe a star that began its life with a mass many tens of times that of the Sun, and that has already passed through a long main phase in which hydrogen in the core fused into helium. In the earlier phase, the star would have been much more compact and hotter at the surface, radiating strongly in the ultraviolet and driving a faster wind. Over time, as hydrogen in the very center was consumed, the core contracted and heated, while layers above it expanded and cooled. The star shifted toward lower surface temperatures and higher luminosities on the diagram that relates brightness and temperature moving into the realm of supergiants and hypergiants. By the time it reaches the present cool extended configuration, the core of such a star is expected to consist primarily of helium and heavier elements held at extreme densities and temperatures by the weight of the overlying material. Around this compact core, nuclear burning no longer occurs in a single central region, but in several nested shells. The innermost still active shell fuses helium into carbon and oxygen, or if helium has already been largely exhausted, carbon, into heavier nuclei such as neon and magnesium. Outside this, hydrogen that remains in layers not fully mixed with the core can continue to fuse in a surrounding shell, adding helium ash to the growing central region. The existence of multiple burning shells is a natural outcome of the way massive stars evolve. Each time the core exhausts its current fuel and contracts, it heats the adjacent layers above the threshold needed to ignite the next reaction, while cooler, more distant layers retain enough hydrogen or helium to continue fusing at lower temperatures. In V766 Centauri Aa, the exact configuration of these shells is uncertain because the current core mass composition and evolution stage are not directly measured. However, the very high luminosity and advanced surface enrichment expected for such a hypergiant point toward a structure in which hydrogen shell burning helium, shell burning, and at least the onset of heavier element burning coexist in a compact region that contains only a fraction of the total stellar radius, yet most of the mass. In this interior, temperatures reach tens of millions of degrees or more, and densities are high enough that matter behaves as a highly compressed plasma. Energy is generated there through nuclear reactions that convert mass into radiation, primarily in the form of gamma rays and neutrinos. The gamma rays are rapidly absorbed and re-emitted by the surrounding material, beginning a long random walk outward, while neutrinos escape almost freely, carrying away some of the energy without interacting strongly with the star. The rate at which nuclear energy is produced is finely balanced against the rate at which radiation carries energy away through the outer layers. If the core generates more energy than the envelope can transport efficiently, the envelope expands and cools until the energy flow matches the transport capacity. If it generates less, the core contracts and heats, increasing the burning rate until balance is restored. This feedback keeps the star in a quasi-static equilibrium on timescales longer than the dynamic timescales of the envelope, even while the detailed structure slowly changes as fuel is consumed and ashes build up. Above the compact nuclear burning region, radiation becomes the dominant means of energy transport for a substantial radial range. In these radiative zones, photons carry energy outward through repeated absorption and scattering by ions and electrons. The temperature drops steadily with radius while the density decreases as well, though much more slowly than in the outer envelope. Here the composition gradually shifts from the heavy element-rich core to layers with more hydrogen and helium that have not yet been fully processed. The gradients in temperature and composition are shaped by both the nuclear burning history and the mixing processes that occur over the star's lifetime. Convection can partially erase sharp composition gradients by dredging up material from deeper layers and blending it with the envelope, while rotationally induced mixing can transport elements along isobars, altering the profile in more subtle ways. In V766, Centauri Aa evidence for surface enrichment in elements produced in nuclear reactions such as nitrogen enhancements, and changes in the ratios of carbon and oxygen would indicate that mixing has brought processed material to the outer layers. Although detailed abundance measurements for this heavily reddened star are challenging, similar hypergiants show such signatures, and models of stars in this luminosity range include mixing as a key process. The presence of multiple burning shells and strong composition gradients also affects the stability of the interior. At interfaces between regions of different composition and density, internal gravity waves can propagate, carrying energy and momentum. In some models, these waves can reach the base of the envelope and contribute to surface variability and mass loss. Inside the shell burning region, changes in the nuclear reaction rates as fuels are exhausted, or as temperature and density change, can alter the structure on timescales that are short compared with the overall lifespan of the star, yet still long compared with the pulsation periods of the envelope. The result is an interior that evolves stepwise, with intervals of relative stability punctuated by structural adjustments that ripple outward. The central core, made of the ashes of earlier burning stages, grows in mass as shells add more processed material. Its radius remains small compared with that of the star, and its density and temperature continue to rise. For a star like V766 Centauri Aa, the core mass at this stage is likely to be many times that of the Sun, though still below the limits at which electron degeneracy or other quantum effects dominate the pressure. As heavier element burning proceeds in shells around this core, the timescales for each stage decrease. Hydrogen burning in the main phase lasts millions of years, helium burning perhaps hundreds of thousands, while later stages such as carbon neon and oxygen burning proceed more rapidly, sometimes over only thousands or even hundreds of years in very massive stars. In the present interior of V766 Centauri A, several of these stages may be active or close to activation, depending on the current core mass and temperature. Although the exact number and detailed arrangement of burning shells remain model, dependent, the general pattern of a compact multi-shell nuclear engine surrounded by a vast loosely bound envelope is robust. This dichotomy between core and envelope defines much of the star's behavior. Deep inside the core and its shells are small, dense, and governed by conditions where nuclear physics and high-energy radiation dominate. Outward from this, radiative and convective zones mediate the flow of energy, gradually diluting it across an ever-increasing volume. At the boundaries between these zones, Opacity peaks and composition gradients can hinder or help energy transport, influencing how steeply temperature falls and how far the envelope inflates. Farther out still in the extended outer envelope described previously, the energy finally emerges as photons that interact with gas and dust in a medium that is close to losing its gravitational grip. Because direct probes of the core are possible, the main constraints on this interior picture come from the star's luminosity, effective temperature, variability, surface composition, and mass loss. The luminosity demands a core and shell structure capable of sustaining a high energy output without immediate collapse or runaway expansion. The effective temperature and radius place V766 Centauri Aa in a region of the brightness and temperature diagram associated with stars that have already ignited helium and possibly more advanced burning in their cores. The variability and mass loss show that the envelope is responding strongly to the underlying energy flow and to the internal structure, while surface abundances reflect the integrated history of mixing and nuclear processing. Models that fit these observables with physically consistent stellar structures converge on a picture in which V766 Centauri Aa is supported by a compact core and multiple nuclear burn-in shells that occupy only a small fraction of its enormous volume. Above them, layers of radiation-dominated and convection-dominated material translate the core's energy into the luminous output seen at the surface. In this sense, the stellar monster, visible as an inflated, unstable hypergiant in the Centaurus arm, is the outer expression of a tightly confined nuclear furnace whose size is tiny compared with the extended envelope, yet whose energy defines every aspect of the larger structure. The life of V766 Centauri Aa begins in the dense interior of the molecular cloud complex, now recognized as part of the GUM-48d region, at a time when that cloud still holds most of its mass in cold dark form. Within one of the thickest filaments, turbulence and external pressure compress a clump of gas and dust until gravity gains the upper hand. As the clump contracts, it fragments into many smaller cores, most of which will become low or moderate mass stars. A few, however, gather enough material to reach initial masses of several tens of solar masses. One of these massive cores will eventually become V766 Centauri Aa. In its earliest phase, while still deeply embedded in the cloud, the forming star accretes gas through a disk and drives collimated outflows that clear narrow channels through the surrounding material. As its mass grows, the central temperature and density rise until hydrogen fusion ignites in the core. The object then settles onto the main sequence as a hot luminous star, most likely of early O type, with a surface temperature of many tens of thousands of degrees and a radius only several times that of the Sun. At this stage, its spectrum is dominated by strong ultraviolet radiation and by powerful stellar winds moving at hundreds or thousands of kilometers per second. The star's light carves the beginnings of an ionized bubble in the surrounding cloud, marking out the region that will later expand into the evolved nebula seen today. During this hot compact main phase, V766 Centauri Aa converts hydrogen into helium in its core at an enormous rate, yet its lifetime in this state remains only a few million years short compared with that of less massive stars. While the core fuses hydrogen, the outer layers respond to the intense radiation by driving a steady wind that removes mass from the surface. Over time, this wind erodes part of the envelope and injects chemically processed material into the nascent nebula. The star's rotation and any early binary interaction can influence this phase, mixing material from the interior toward the surface and possibly altering the mass loss pattern. As hydrogen in the core becomes depleted, the central region contracts and heats, while the outer layers begin to expand. the star leaves the main sequence and moves across the diagram that relates luminosity and temperature evolving into a blue supergiant with a somewhat larger radius and slightly lower surface temperature, but with an even higher luminosity. In this phase, helium fusion may ignite in the core, while hydrogen burning continues in a shell around it. The stellar wind remains strong and fast, and together with radiation, it pushes the ionized bubble farther into the surrounding cloud, enlarging the cavity that will later appear as a ring of glowing gas in observations of the region. Whether V766 Centauri Aa next passes through a long, fully developed red supergiant stage, or instead experiences one or more shorter excursions to cooler temperatures, is not yet firmly established. Models of very massive stars in this mass and luminosity range suggest two broad possibilities. In one, the star expands greatly and cools at its surface, becoming a red supergiant with an extended cool atmosphere and heavy mass loss. In the other, strong winds and internal mixing limit the expansion, so that the star spends more time as a blue or yellow supergiant, and only briefly attains red supergiant conditions if at all. The current classification of V766 Centauri Aa as a yellow hypergiant and its location near the empirical boundary, where very luminous stars appear to avoid the coolest temperatures, hint that it may have spent at least some time as a red or very cool supergiant and then evolved back toward warmer temperatures, or that it has executed wide loops in temperature while maintaining a high luminosity. Surface chemical signatures where measurable support the idea that deep mixing has occurred. Enrichment in nitrogen and relative depletion of carbon at the surface, seen in other hypergiants and in related luminous stars, imply that material processed by hydrogen burning in the core has been transported outward. In V766 Centauri Aa, such enrichment would indicate that the star has already completed a substantial portion of its helium-burning phase and has experienced extensive internal mixing, whether through convection rotation or binary interaction. As it evolves away from the redder, cooler side of its path, the star contracts somewhat, and its effective temperature rises into the range characteristic of yellow supergiants and hypergiants, while its luminosity remains roughly constant or increases slightly. The envelope, however, has been profoundly altered by prior mass loss. A large fraction of the original hydrogen-rich envelope may already have been removed by winds during the earlier stages, leaving a star with a more massive core and a thinner, more unstable outer envelope. The reduction in mass combined with the still high luminosity brings the ratio of radiative force to gravity closer to unity in many layers, making the star more prone to pulsations, inflation, and episodes of enhanced mass loss. At the same time, the surrounding nebula records the earlier phases. The ionized gas and the shape of the cavity trace the integrated output of ultraviolet radiation and winds from the hot phases, while the dust and molecular structures in the compressed ring and inner cloud include contributions from the later cooler winds and eruptions. V766 Centauri Aa's past main sequence and blue supergiant stages have already contributed to this environment by heating, ionizing, and enriching the gas. As it moves into the yellow hypergiant domain, its radiation shifts more toward the visible and infrared, and its wind slows but grows denser, adding new layers of dust-rich material to the circumstellar envelope and to the interior of the cavity. The star's radius during these transitions does not follow a smooth, monotonic path. Instead, theoretical tracks for very massive stars in this regime show that they can expand and contract in response to changes in the core burning stages and in the envelope's opacity. When helium burning in the core begins and stabilizes, the energy production may briefly cause the star to contract slightly and become hotter at the surface. Later, when helium is exhausted in the core and burning moves outward into shells, the core contracts further and the envelope responds by inflating. Opacity peaks associated with heavy elements and partial ionization zones help support this inflated envelope, as described earlier, and make it easier for the star to reach large radii. V766 Centauri Aa appears to be in one of these inflated phases now, with an envelope extended to many hundreds, or perhaps around 1,000 solar radii. During its earlier evolution, the star may have crossed the region of the diagram associated with luminous blue variables, a class of unstable hot stars that show strong variability and eruptions. Whether it experienced classical luminous blue variable type outbursts with dramatic increases in brightness and mass loss, or only milder instabilities, is not firmly known, because any such events would have occurred before modern monitoring began, and their direct signatures could be hidden by subsequent evolution. However, the existence of a massive dusty circumstellar envelope and the current hypergiant state are both consistent with the history that includes strong mass loss episodes of some kind. Binary interaction may also have influenced the path. If the close companion now suggested by interferometric observations has been present since the early stages, its gravity could have altered the rotational profile, enhanced mixing, and at later times drawn off part of the envelope as the primary expanded. Such interaction can remove mass from the primary more efficiently than winds alone, and can change the relative durations of blue, red, and yellow phases. It can also help explain the presence of a common envelope configuration in the present state. The wider association with the blue supergiant companion HR 517. 1b marks the fact that the system formed as part of a small group with more than one massive star evolving in parallel, each affecting the shared environment. Over the course of its life so far, V766 Centauri Aa has therefore moved from a compact hot main sequence star that excavated an ionized bubble in its birth cloud through one or more stages as a blue and possibly red supergiant into its current role as an inflated yellow hypergiant surrounded by a massive circumstellar envelope and embedded in an evolved nebula. At each stage, the core has progressed through successive nuclear burning phases, building up heavier elements and increasing in mass, while the envelope has become increasingly extended, mixed, and depleted by winds and possible binary-driven mass transfer. The present configuration, with its tenuous outer layers, dense wind dust, rich envelope, and complex variability, reflects the cumulative effects of this past evolution rather than a single isolated event. Although details such as the exact initial mass, the precise sequence of temperature changes, and the strength and timing of any eruptive episodes remain uncertain, the combination of stellar models, observed luminosity, and temperature, circumstellar structure, and environmental impact all support a history in which V766 Centauri Aa has already undergone major structural changes and extensive mass loss, leaving it now as a highly evolved swollen star whose past hot phases are written into the nebula around it, and whose current unstable envelope is the latest outcome of that long internal transformation. In its present state, V766 Centauri Aa stands as a highly evolved, very luminous star with an extended unstable envelope and a compact interior in which nuclear reactions proceed in several shells. This configuration cannot persist indefinitely. The core continues to grow in mass and to contract as it converts lighter elements into heavier ones, while the envelope continues to lose mass through dense winds and possible binary-driven outflows. Stellar evolution models for stars with similar luminosities and inferred masses indicate that the remaining lifetime in such a phase is short, compared with the earlier history, likely no more than a small fraction of 1,000,000 years. During this interval, the internal burning stages proceed rapidly as each successive fuel supplies energy for progressively shorter times. Helium burning in the core, if still active, moves toward exhaustion, giving way to carbon burning and then to heavier element burning in shells that encase an increasingly compact core. With each stage, the core contracts further, its density and temperature rise, and the envelope must readjust to the changing gravitational and radiative conditions. As the core evolves, the envelope of V766 Centauri Aa may undergo further structural changes. Some models predict that very luminous yellow hypergiants can contract and heat at the surface, once again moving back toward higher temperatures on the diagram that relates brightness and temperature. In such cases, the star may evolve into a hotter blue supergiant, or into an even more compact stripped star resembling a Wolf-Rayet star, especially if mass loss has removed most of the hydrogen-rich outer layers. Other models suggest that the envelope can remain inflated for much of the remaining lifetime, punctuated by episodes of contraction and expansion as the star crosses regions of instability. Which path V766 Centauri Aa follows depends sensitively on its current mass composition rotation and on the strength and geometry of its mass loss, all of which carry significant uncertainties. The presence of the close companion and the possible common envelope configuration add additional branches to the evolutionary possibilities. In one scenario, continued mass loss driven by radiation and binary interaction gradually removes the outer layers without causing a catastrophic event until the core reaches the conditions for collapse. In another, the companion may spiral inward through the envelope as friction transfers orbital energy to the gas, leading either to ejection of the envelope in a relatively brief common envelope phase or to a merger of the two stars. Envelope ejection could produce a dense asymmetric circumstellar shell, while a merger could create a single more massive rapidly rotating star with altered internal structure. At the present time, available observations do not fix the binary parameters tightly enough to choose among these possibilities, though the evidence for extended structure and strong interaction shows that the binary configuration is likely to influence the later stages strongly. Regardless of the detailed path, the end point of the evolution of V766 Centauri Aa is expected to be a core collapse event. Once the core has built up a sufficient mass of heavier elements and has exhausted the nuclear reactions that can provide thermal pressure support, it will no longer be able to balance gravity. The core will then contract rapidly on a dynamical timescale, reaching densities where nuclear matter and degeneracy pressure dominate. The sudden collapse and subsequent bounce, together with neutrino emission and other processes, are expected to launch a shock wave outward through the surrounding layers. If sufficient energy is deposited in the overlying material, the star will explode as a core collapse supernova, ejecting the remaining envelope and leaving behind a compact remnant, most likely a black hole in the case of such a massive progenitor. If the envelope mass at the time of collapse remains large and extended, the outgoing shock and radiation will interact strongly with the circumstellar medium. Dense gas and dust close to the star can produce a supernova with strong signatures of interaction, possibly resembling the class of supernovae with narrow hydrogen lines formed in a dense, slow wind. If the envelope has already been mostly removed, the explosion may appear as a more stripped event with weaker hydrogen features, or with a spectrum dominated by helium or heavier elements. In extreme cases where mass loss and binary interaction have been very efficient and the core mass is high, some models allow for the possibility that the core may collapse directly to a black hole, with only a faint or absent optical display. For V766 Centauri Aa, the current uncertainties in mass envelope structure and binary interaction mean that the exact character of the final event remains open, but the general expectation of core collapse and black hole formation is robust for stars of such high initial mass and advanced evolutionary state. Long before this final collapse, V766 Centauri Aa already plays a role in defining the empirical limits within which massive stars can exist as extended luminous objects. On the diagram that relates stellar luminosity to effective temperature, very luminous stars are observed to avoid a region at cool temperatures, where the combination of high brightness and low surface temperature would demand envelopes so extended and radiation-dominated that they would be unstable. This empirical boundary, often called a luminosity limit for cool supergiants, marks a region where stars with sufficiently high luminosity either do not form or do not remain long. V766 Centauri Aa lies close to this boundary, with an inferred luminosity of several 100,000 solar luminosities and an effective temperature in the range characteristic of yellow hypergiants. Its radius and unstable envelope show how a star can approach this limit, while developing strong mass loss pulsations and complex atmospheric structure. By comparing its observed properties with those of other luminous cool stars and with theoretical models, astronomers refine estimates of how close to the radiative balance point stars can operate. The mass loss rates, wind velocities and dust production seen in V766 Centauri Aa give practical measures of how an envelope behaves when radiation pressure nearly offsets gravity, and of how rapidly such a star can shed mass to move away from the most unstable regimes. The system also contributes to understanding how binary interaction functions near stellar limits. A common envelope phase in a star as luminous and extended as V766 Centauri Aa tests theories of how orbital energy is transferred to gas, how efficiently envelopes can be ejected, and what kinds of remnants and separations result. Observations of brightness, variations, asymmetries in the resolved disk, and changes in line profiles over the proposed orbital timescale provide constraints on models of common envelope evolution for very massive stars, a regime that is difficult to explore in detail by theory alone. The wider association with the blue supergiant companion and with the surrounding cluster of less massive stars, embedded young objects and nebulous structures offers an additional context. The composition of the gas in the GUM-48d region, the enrichment in elements such as nitrogen and oxygen, and the distribution of dust and molecular material all reflect the integrated feedback from massive stars like V766 Centauri Aa over millions of years. As the star continues to lose mass, it adds more chemically processed material to this reservoir, contributing to the pool from which future generations of stars may form. After the eventual core collapse, the explosion, if one occurs, will further enrich the region with heavier elements synthesized in the deepest layers, and will drive shocks through the molecular cloud, possibly compressing gas and triggering new star formation in more distant parts of the complex. In this way, V766 Centauri Aa participates in the larger cycle that connects massive stars' nebulae and the formation of new stellar systems. On shorter timescales, accessible to human observation, the star's current state provides a laboratory for studying the physics of extreme envelopes. Continued monitoring of its brightness at multiple wavelengths, high-resolution spectra of its lines, interferometric imaging of its resolved disk, and observations of its circumstellar dust and gas in the infrared and radio domains all add pieces to a picture of how very luminous cool stars behave near the limits of stability. Changes in its variability pattern, shifts in spectral type, or alterations in the circumstellar environment over the coming decades could signal transitions into different evolutionary stages, such as further contraction toward hotter temperatures, or episodes of enhanced mass loss that precede major structural adjustments. Each change helps test and refine theoretical models, reducing the uncertainties in the predicted paths of similar stars. For now, V766 Centauri Aa remains an inflated, unstable hypergiant embedded in an evolved nebula in the Centaurus arm, losing mass through dense winds, interacting with companions, and operating near the empirical limits of size and luminosity for a star supported by its own internal nuclear reactions. Its future encompasses further internal evolution of the core, continued reshaping of the envelope, and an eventual core collapse that will end its life as a luminous star. Its role in the present is to show in detail how a massive star behaves as it approaches those end stages, and how the combination of extreme luminosity extended structure, mass loss, and binary interaction defines a practical boundary in the space of possible stellar configurations.